Hi, in this work we set to suggest type annotations to partially typed programs. Python allows optional type annotations. Take this simple example here. The parameter points is annotated as a list of point, whereas the print points function has a return type of none. The goal of Typilus is to predict these type annotations. So in this example, the type annotation of the parameter points. In many cases where we have partial context, this is an under-constrained task. For example, here a formal method might suggest that points is an iterable whose elements are tuples or arrays of at least two elements. But it wouldn't suggest that this is a list of points, which is natural within this context. For the rest of this talk, we refer to this task as probabilistic type inference. Our goal is to help developers to progressively annotate their programs with types so that traditional type checking can be effective. When humans reason about a program, they use uncertain information about that program. So, for example, if they see a variable named counter, they realize that this is a non-negative integer without even seeing a type annotation. Or when they see num oranges to be added to num bananas, they realize that these two things are integers, but they are probably not compatible. So the goal of our research is to use machine learning to learn and detect patterns in the code that will allow us to probabilistically reason about types and type relations. Towards this goal, we're going to use graph neural networks, GNNs. It's a type of a neural network that operates on graph structures. Given an input graph representation, the GNN computes an output graph representation, capturing patterns about the structure of the graph along with any information stored in the nodes and edges. Typilus represents source code as graphs and uses a GNN to compute an output representation. Specifically, it uses the output representations of the node that correspond to Python symbols, such as variables and functions, to represent the type properties of these symbols. We call the output representations of these nodes type embeddings. But first, we need to define a graph representation of our source code. So, how do we construct it? This is a design task with no unique solutions. At a high level, we follow previous work. First of all, we include the sequence of tokens in the code. We also include the abstract syntax tree. As you can see here, we get a very simple graph that contains syntactic information. We also add edges that indicate data flow. Here you can see the next may use edge, indicating how a variable may be used within the simple program. For example, variable a may be assigned in either branch of the if-else statement. Such edges provide useful semantic information about the program. In our graph representations, we also introduce extra nodes. The symbol nodes, the black nodes here, connect all appearances of an identifier to that node. So here, for example, all appearances of variable b are connected to the symbol node b. We keep repeating this process by adding more syntactic and semantic edges and nodes. At the end of the day, we're interested in predicting the type annotations of specific symbols. So we use the graph neural network to process this graph and take the output representations of the symbol nodes as the type embeddings. These type embeddings are d-dimensional vectors. They live in a type space. The type space can be thought as a continuous relaxation of the space of all possible types within Python. The goal here is to learn a graph neural network that learns to create a type space that preserves, as much as possible, the type properties of the code. To predict type annotations, we use a simple meta-learning framework. We first build a type map. For identifiers with type annotations or identifiers whose type we can statically infer, we compute their type embeddings. Then we associate the locations of these embeddings to those types. We call this a type map. Crucially, we can map types in the type space that were not included in the training data. This allows us to dynamically learn new types and is the essence of our simple meta-learning framework. To achieve this, we simply have to ask our graph neural network to predict the type embedding of the symbol with a new type. We can then update the type map to associate the computed type embedding with a new type. At test time, the GNN computes type embeddings for all identifiers with no type annotations. Typilus then queries the k nearest neighbors and suggests their types. Finally, a type checker filters type incorrect suggestions. So far, we assume that the graph neural network has been trained and that we have a consistent and useful type space. But how is this achieved? We use a variant of triplet loss. As the triplet loss equation suggests, given two symbols S and S plus with the same type annotation and a symbol with a different type annotation S minus, the training objective nudges the graph neural network to learn type embeddings such that the symbols with the same type are close by and the symbols with the different type annotations are far away. It's as if each symbol attracts symbols with the same type annotation and repels type embeddings of symbols with different type annotations. In practice, we employ a variant of triplet loss that learns from more than 3 symbols at each time and considers larger sets of symbols. We call this the typespace loss, L space. Note how the typespace loss differs from the commonly used classification loss. A classification objective would learn to partition the type embeddings into type annotations, leaving no regions representing previously unseen types. Instead, L-space merely requires symbols with the same type to be close by, allowing for regions in the type space to represent new, previously unseen types. To retrieve the full Typilus loss, L-Typilus, we then carefully combine L-space with the classification loss. Specifically, we have the classification loss that takes each type embedding, performs a linear projection to a new space, and classifies the projected embedding to the class of the type parameter erased type. For example, if the type of a symbol S is list of strings, then the projected type embedding will be classified as list. This additional loss acts as a consistency layer, introducing knowledge about parametric types. Having described some of the inner workings of Typilus, let's now turn into evaluating it. As a machine learning-based method, we need data. We get 600 open-source Python projects from GitHub that use Python type annotations. Given the large amount of duplicates that appear in automatically scraped corpora, we first deduplicate our corpus. This gives us about 100,000 files or graphs and 250,000 type annotations. These annotations are highly imbalanced, with common types accounting for a large percent of the data, but with a heavy tail of rare type annotations. To evaluate our approach, we test two different code representations. A sequence-based representation that uses bidirectional recurrent neural networks to parse through the tokens and predict the types of the symbols. The graph-based representation is the one we showed earlier. Both representations can be combined with 3 different losses we previously discussed. This gives us 6 model combinations. First, we evaluate the ability of our models to retrieve exactly the ground truth annotations where they exist. Here we saw the results in our test set averaged over 2 runs. The graph-based models perform better than the sequence-based models. We also see that the models that use classification perform the worst. Typilus, that combines our meta-learning framework and classification, performs the best. When we split the types into common types, those that appear frequently, and rare ones, we see a big performance gap. The type space allows to better predict rare types, but there is still much room for improvement. The difference between Typilus and graph-to-class and graph-to-space suggests that the classification loss that we added helps a lot with the common types, at the cost of a slight degradation of the performance on rare types. Looking at the precision recall curves, we see that Typilus achieves a better precision recall trade-off. Here, the black line shows the type-neutral suggestions, meaning that if we were to replace the original annotation with that new suggestion, no new type error would be yielded. For a recall of 60%, Typilus achieves high precision of about 95%, whereas the graph-to-class model, on the left, is much worse. So far, we measure the performance of predicting the ground truth type annotations. Here, we use developers applied annotations as our ground truth, which is approximate, since developer annotations can be wrong. We will discuss a few such cases later. Before further evaluating Typilus, let's look at an ablation study of our Python graph representation, which is the input of the graphical network. First, we see that just using the names of the symbols can get us an exact match of 38%. This is quite substantial and interesting. The names of the variables, parameters, and functions seems quite indicative of the type of the symbol. Although traditional type inference methods cannot take this information into account, probabilistic machine learning-based type inference methods can use it effectively. We also see that removing the data flow edges doesn't affect the predictive performance of our model, suggesting that the ways data flows within a program isn't necessary for the task. This is not unexpected, given how traditional type checking and inference works. To further evaluate Typilus, we employ two widely used optional type checkers, MyPy and PyType, and use them as oracles for the accuracy of our predictions. Given the optional nature of Python's type annotations, some of the suggestions simply cannot be disproved by type checkers, and they still might be incorrect. Despite this, they are reasonable oracles, and we use them to establish performance here. For each graph, we compute the type embeddings of all symbols, even those that originally didn't have a type annotation. We then apply separately each type annotation to the code and check it. The table shows the percent of suggestions that each type checker considers valid. Specifically, in places where we originally had a type annotation, but Typilus suggests an alternative one, the type checkers find it acceptable 63 to 85% of the time. This shows that evaluating on the ability to predict and ground truth annotation might miss valid suggestions. Additionally, for locations where previously there was no annotation, 83 to 89% of them are acceptable by the type checkers. Although it might be that some of the suggestions simply cannot be disproved by the optional type checkers, this evaluation gives us some confidence that Typilus makes valid suggestions in locations where we don't have ground truth annotations. We now take a more qualitative look at Typilus suggestions. First, while we were doing error analysis, we observed some highly confident suggestions that seemed plausible. After manually checking them, we realized that some of the ground truth type annotations were incorrect. Indeed, two popular open source projects merged our pull requests fixing these annotations. One is shown in this slide. Here, Typilus found that it is very unlikely that the shown parameters are floats, but should instead be integers. The reason that these faulty annotations were not captured earlier is due to the nature of optional type checkers, which were not able to disprove these user-supplied type annotations. This further illustrates the importance of machine learning-based methods for optional typing, where the lack of guarantees impedes traditional type checkers from finding errors. Of course, not all type suggestions are correct. Some mistakes have to do with the deeply structured nature of types, or with the partial context. Here, we highlight one interesting case. Typilus suggests for the parameters scores and offset the type torch.tensor, but the ground truth annotation is different. Interestingly, torch.tensor and mx.nd.nd array are classes representing n-dimensional arrays, but in two different deep learning libraries. This suggests that conceptually, Typilus represents such arrays in a close-by location in the type space, capturing some semantic similarity between those two classes. We recently released Typilus as a GitHub action that can be seamlessly integrated into GitHub workflows. The Typilus action reviews the code and submits comments when a user creates a pull request. Typilus suggests adding type annotations when it can make confident predictions. For example, here in the slide, Typilus suggests to annotate the parameter name as a string and the parameter config as a dictionary of strings to any. If you have a Python project, consider trying this out. Before concluding, I want to mention three concurrent works that appeared while our paper was in submission: LambdaNet, OpTyper, and Typewriter. These three papers appeared at the same time as ours and share some similarities, but also have many new interesting ideas that could be combined with the ideas presented here. Going back to Typilus and the broader research area of probabilistic type inference. I believe this is a very interesting area that combines the formal constraints found within programs with powerful neural pattern recognition methods. However, there is still a lot that needs to be done to better fuse type checking and type inference with neural methods. There is also a big opportunity for programming language research to contribute to machine learning. Despite the expressiveness that Typilus typespace has, existing methods cannot capture exactly the concepts captured in types. Taking ideas and concepts found in programming language research might help deep learning methods overcome limitations of existing neural representations. Thank you for listening to our talk. All the code and data generation scripts can be found in our GitHub project.